Welcome back to our next topic in rotational motion. After kinematics for linear motion, the next idea we talked about were forces and dynamics, the why things were moving the way they were. And so we're going to repeat that idea with rotational motion, and we're going to introduce the topic of torque. And torque describes the effectiveness of a force in producing rotational acceleration. So essentially, we can think of torque as a force that causes rotation. So force is a vector that produces linear acceleration A, and torque produces angular acceleration alpha. And there are three factors that determine how much torque is produced. Before we look at that, I want to look at the visual down here, and this is going to help us define those three factors. So we're going to imagine that this image shows a door, and the axis of rotation that I've labeled here on the left represents the door hinge. So that's the point at which the door pivots around. Well, first of all, if we're trying to open the door, we have to push on the door, right? There has to be a force to cause the door to move. So the first thing that affects or would contribute to a torque is the force itself, the magnitude F. So the magnitude of the force. We have to push on the door for the door to open. Looking at our picture here, another thing that affects our ability to open the door is where on that door are we pushing. If we push on the door hinge, that door's not going to pivot open, is it? So we have to be some distance away from the axis of rotation, and the amount of that distance will affect the torque that we produce. So the next factor is the distance from the axis of rotation. The distance from the axis of rotation, and we're going to label that R, lowercase r. All right, the last thing that will affect the torque or the ability to open the door is what angle that we are pushing on the door at. So the angle relative to the force and to the direction of the lever arm, this vector R. And so the angle at which the force is applied will also affect the ability to produce a torque. All right, so those are our big ideas. Let's go ahead and write out this mathematical relationship, our equation. So torque is going to be represented by the Greek letter tau, and the equation for torque is RF sine theta. So R, kind of that lever arm, or the distance from the axis of rotation to where the force is acting. F, the amount of the force itself. And sine theta, that angle between R and F. And what we're picking out with F sine theta is we are really looking at the force perpendicular to the lever arm. I'll draw that here in just a second. The force perpendicular to the lever arm. So when we take the sine theta here, we are getting how much force is pointing perpendicular to our door versus the total amount of force used. So this idea, if we are pushing parallel to R, we're not going to be able to produce a torque. If I push on this way, we're not going to be able to cause that door to rotate. So we have to have some amount of perpendicular force to cause that. All right. Next idea are units for torque. Well, we have a distance and we have a force. And so we typically switch the order of that for our unit. It's going to be Newton meters. So Newton times meters. And that is our unit. The last idea is kind of our convention, what direction we take to be positive. So if our torque is causing a counterclockwise rotation, we're going to call that the positive direction. So if it's causing our object to rotate this way around, like our example here with the door, that would be counterclockwise. That's an example of the positive direction. If the torque causes the object to rotate clockwise, that's an example of a negative torque. It's rotating in the negative direction. All right, and that is our introduction to torque.